Okay, I'm coming back. Okay, thank you. Thank you, Jalim.
Yeah, students.
Okay, and the main, how to say, the only one fundamental for this class, I mean for today topics, is the relationship between the position, the acceleration, and the velocity in one-dimensional. Yeah, maybe you can switch the order: position, velocity, acceleration, but I try to write in this way because sometimes you don't need to relate the velocity to the acceleration so that you can get the relationship between the position and acceleration. But sometimes you don't need to consider about the velocity. You can find the direction relationship between the position and the acceleration. But for the position, in one directional, in general, the position, is represented by the vector, position vector r. But for one directional, sometimes we can represent the position by the distance and the direction of the distance is just represented by the sign plus and minus. As I mentioned, if you consider the motion on a linear motion, if your position of the point P is on the right-hand side of the reference point, you can write the distance and indicate the direction by plus or minus. This is the position. And velocity, the unit, the SI unit of the velocity is meter per second. By the unit, we can get some hint that the velocity is the time derivative or the ratio of the length and the time. If we plot the relationship between the position and time, the velocity, the velocity is the time derivative of the position divided by time. Or in one directional, it can be the time derivative of the distance by time. But yeah, the distance is the vector, but this vector, the meaning of this vector, it just has plus and minus to indicate the direction. If we consider only the magnitude of the velocity, it will be the time derivative of the distance divided by time. You may be familiar with the average speed. The average speed consider only the magnitude of the change in the displacement or the distance by time. With this, we usually use it when the change in the velocity is not so significant against the time. We try to assume it as an average speed during the delta t. But in our class, most of our problem, we rarely use the average speed. But in our class, before this, you may also familiar with the average acceleration, which is the change of the speed by time. In our class, we consider the actual derivation, the instant derivation, not the average rate. So yeah, let's see. For example, if the position is plotted against time, the position in meter, the time is measured in seconds, and the slope at any point, will be the speed. And from this, can we write down ds is equal to v dt. So what if we do the integral on both sides? The integral of the distance and the integral of the velocity against time. The integral of the distance begin from the distance at time t equal to 0 and the distance at time t. The velocity is also integrated from t 0, which is equal to 0, or maybe don't need to be 0, and time t, which means s subtract by s0 is equal to the integral of v against dt. If we have a constant speed, it's just only v t minus t0. If v, or the speed, is constant, what if the V is not constant? We should have we will come back to this page, but we will see the plot between the acceleration and time. Okay, to talk about the acceleration, we will talk about the change of the speed and time. The change of the speed and time. At any point of time, the slope of the speed plot against time. The slope of the speed plot against time is defined as acceleration. So acceleration have the unit of meter per second square, and acceleration is the change of the time derivative of the speed of the velocity divided by time. But for the scalar consideration, the magnitude of acceleration is the change of the distance, no, the change of the speed by time. But we know that the speed is the change of the distance by time. So acceleration can be or the second time derivative of the distance by time. We may be familiar with this, but another useful relationship that you need to maybe try to remember is we can have the relationship between the velocity that change against the distance, and by the chain rule, you have the ds by dt. By this is velocity, and you can rewrite this equation by a ds equal to v dv. Many times you can solve the problem by using this relationship. We will see the advantage of using this relationship in our example. Sometimes we can do the integration of the acceleration against the distance, and it will equal to the integration of v dv. We need to consider from the distance s0 when time equal to 0, and the final distance, wait a second. Okay, sorry. And on the right hand side, the velocity is also being integrated from the initial velocity to the final velocity. But in this case, we may need to find the function of the acceleration as a function of the distance. So please keep in mind, when you see the problem, and in that problem, you know this information, the relationship between the acceleration that change against the distance. If we can find the function of acceleration as a function of the distance, and we need to find maybe the initial velocity or the final velocity, many times we can take advantage of this relationship. But if you don't want to remember the relationship, you may begin from the basic idea that the acceleration is the dv by dt, and just apply the chain rule here so that you can compose this relationship. Many times back to my undergrad time, when I need to do the exam in the dynamic class, I also just remember the basic relationship and try to write down the relationship and see what are the information given in the exam question, and try to think in which relationship I should use to solve the problem. We are going to jump back to the previous page, but before we going back to that, let's zoom in to the basic relationship here. We can write down that ADT is equal to dV, which means if we do the integral from V0 to V, it should equal to the integral of A dt from T0 to T. So what does it mean? It means that V minus V0, the right hand side, should equal to if in our case we consider the constant acceleration. If in this case we consider the constant acceleration, okay, Panat, do you have any question?
Sorry, Mr. Teacher.
Oh, okay. And in the case of constant acceleration, what we can get from here is if the acceleration is constant against time, we can bring it out from the integral, and the integration will be just t minus t0, and it seems to be like velocity is equal to the initial velocity plus the acceleration multiplied by the time change. If the time change can be delta t, or if t0 is begin from 0, it should be like the instant velocity is the initial velocity plus acceleration multiplied by the time. But this should be marked that the acceleration need to be constant so that we can get this, we can use this relationship. But in some special case, especially in this course, which is, how to say, have some extension from your study of mechanics in the physics class, we have some case that acceleration don't need to be constant, but we may relate to the distance instead of the time. But by this, I hope you still remember in the high school time, you may remember V equal to U plus AT. Velocity is initial velocity plus acceleration multiplied by the time. Okay, we will use this to put into the previous page. V equal to V0 plus AT. Here, if V is not constant, the S subtract by S0 will equal to the integral of V equal to V0 plus AT and dt from T0 to T. So yeah, we can do the integral and obtain this relationship. S, or the distance, is equal to the initial distance plus initial velocity multiplied by the time change and plus the acceleration multiplied by t squared per 2 and the t equal to T0 and T. But this case, be careful. The acceleration is constant. Okay, what if the T0 is 0? You can get the simple relationship that S equal to S0 plus V0 T plus 1 per 2 AT squared. Maybe from your high school time, you use S equal to UT plus 1 per 2 AT squared. Yes, these are the relationship. So it seems like these two slides are the review for you to get the idea of the relationship between position, acceleration, and velocity. But what news that is important, and you can see how applicable is this relationship in our example, is this one. This is a new one. Yeah, AdS equal to VdV. If you don't understand what I teach and need more extensive explanation, everything on this, all the plot and all the relationship, is also described in the textbook. So yeah, let's go on the example. For me, every time when we see the complicated explanation of the problem, I will try to read through and check what we know from the problem explanation. A particle moves along the positive x-axis with an acceleration ax, but in this case, ax is not constant. but it changes linearly against the distance x, and they show in the plot. So read until here. You should notice that the acceleration is not constant. So maybe the relationship that we study in our high school time, in the physics 1 time, maybe it's not applicable, or we cannot solve it easily using that relationship. But what the information give, they have the relationship between the acceleration and the distance. So maybe the new one that we just talked about should be useful, but let's see. And when I read the problem, I will try to write what they give. They give the acceleration as a function of the distance in x direction. And if the velocity at x equal to 40 is equal to this, the velocity at x, I always try to write this in the SI unit. Also, 40 millimeter is 0.04 meter. So velocity at this position is equal to 0.4 meter per second. And what we need to find, the velocity at x equal to 0.12 meter. So yeah, our solution, as I said, what the problem gives is the acceleration that change against the displacement. So from the basic relationship, we know that acceleration is equal to dv by dt. By the chain rule, is dv by ds and ds by dt. So we have v dv by ds. Does that make sense? And yeah, we have a ds equal to v dv. And the integral for both sides of the equation, integral a ds, but we know that the displacement that we are talking about is in the x direction, in one dimensional. So we can replace the displacement by the distance in x direction. And yeah, velocity is also in x direction. And the boundary of the integration, we may consider the x beginning and x at the final, so that we can find the velocity at the final, because we know the velocity at this point. So the limit of the integration is from x equal to 0.04 meter to 0.12 meter. And the limit of the integration of the velocity, we have the initial, no, not the initial velocity, but the velocity that correspond to the position here is 0.4 meter per second. This is the velocity when x equal to 0.04, which is correspond to this. And here is also the velocity that is unknown, but is the velocity at x equal to 0.12, which is correspond to the limit of the integration on the left hand side. So on the right hand side, it seems like we don't have anything to be concerned about, because we know that the integration of v dv is equal to v squared per 2, and by the limit of the integration v0, v1, for example, we don't have a problem. For the right hand side, we have one value that we know and another value that is the unknown that we are going to find to solve for. But for the left hand side, we need to do the integration of the acceleration against the displacement x. The problem gives this information, the ax as a function of x, but the problem doesn't give us the mathematical expression of ax as a function of x, but they give us the plot. So how can we compose the mathematical description of the ax against x? If we see in any point of x, we should find ax as a function of x. So the idea is to use a similar triangle. Similar triangle may be A, B, C, similar to A, D, E. I hope you can get the meaning. And yeah, by the similar triangle, we can write down the relationship that A subtract 2, A subtract 2, which is this distance divided by distance. This distance is x subtract 40 millimeter. 40 millimeter. The small triangle, the vertical displacement divided by the horizontal displacement in the plot. And for the big triangle, it should be the vertical distance here and the horizontal distance here. So the vertical one is 4 subtract by 2. And the horizontal one is 0.12 subtract by 0.04. And yeah, we need to write A as a function of x. It should be ax, right? As a function of x. Can we do that? Here is 0.08 and here is 2. So 2 divided by 0.08. What is 2 divided by 0.08? You need to help me.
25 ครับอาจารย์
Okay, thank you. Thanks a lot. I cannot find my calculator. Okay, so AX subtract by 2 is equal to 25 multiplied by X subtract by 0.04, isn't it? Okay, and we have AX equal to this will be 25x subtract by 1, right? And plus 2. So AX equal to 25x plus 1. Okay. So this is the acceleration as a function of x. So we may need to continue here. So the integration of 25x plus 1 dx from 0.04 to 0.12 is equal to, on the right hand side, is v square per 2 of v0, which is 0.4 to the v that we want to find. And yeah, the integration of the left hand side, we're going to have 25x squared per 2 from 0.04 to 0.12, and plus the second term is x, also from 0.04 to 0.12. It should equal to v squared per 2 subtract by 0.4 square per 2. And now, yeah, you can substitute the limit of the integration into this, and also, yeah, by arrange the equation, finally, we will get the velocity at the position of x equal to 0.12 that we want. And this is my suggest solution for this. Please take your time to review this example. Do you have any question on this example? Okay. Okay, the next example. Well, this is my fault. I mean, let's try to make it to be like our family unit instead of using the yard. Well, my pen also have problem. I cannot write. What happened? Wait a second. Okay. Instead of using the yard, we try to make it to be like meter. Should be better, right? And second. Okay, it's fine. So just change the distance unit to be meter so that we have the SI unit that we familiar. So what they give from the problem, the information that is given from the problem is a sprinter reached its maximum speed. Wow, the maximum speed also inch per, oh no, I'm sorry. Okay, they reached the maximum speed in 2.5 seconds, and they start from rest with a constant acceleration. So start from rest means v0 equal to 0, and the time that corresponds to the Vmax is equal to 2.5 seconds, and the overall time is 9.6 seconds, and yeah, the distance, the total distance, maybe the total distance or the x total, x final is equal to 100 meter, and the time that he complete the distance of 300 meter or the time final, it also 9.6 seconds. Here are what the problem gives to us, and what they want is we need to find the maximum speed. This problem, it seems to be like nothing related to our robotic class. Why we need to consider the sprinter running on the track, but they give some constraint that somehow similar to our application. For example, if we want to drive your robot arm, if you want to drive your robot arm with one distance, and you want it to go to hit that position by one limit of time interval. And yeah, you know that your driving capacity of the driver circuit can make your system start from the rest to the target speed within the limitation of maximum speed by one specific response time. By the same configuration of the problem like this, you can apply the same method. You're gonna solve this problem to one like trajectory planning, the simple trajectory planning in one directional of the robotics problem. The idea is you need to decide the velocity profile, and the maximum velocity is one thing in the velocity profile that you need to decide in your problem. Let's make the problem be more easy to understand by sketching something. We have the sprinter we have the relationship between the velocity and the time. Reach maximum speed. I think one thing that missing. No, it's not missing. Constant acceleration. Do you see it? This is important. Constant acceleration, which means if we plot the speed by time, the sprinter begin from v equal to 0 or start from the rest v0 equal to 0. Okay, he start from the rest with a constant acceleration. Constant acceleration means the slope of the velocity against t. The slope is a constant, is a linear profile like this. And when he hit with the maximum speed, he cannot go faster than that. He needs to maintain that maximum speed until he reaching the goal of the track. And which means we have the T final. What? There is some problem. Wait a second. Oh no. Wait a second, I'm sorry, but we can deal with it. Can you see my share screen? Can you hear me?
Yes.
Okay. Okay,ครับ. I'm sorry, I have some crash on my PC, but okay. What we had was my PC was crashed, but maybe in the Zoom record it won't have problem. We may recheck it in the record, but what we was drawing was the velocity as a function of the time, and the sprinter accelerate his pace to the max speed. It go to his max speed and go until reaching the final time to the target of the track. And at that final time, we know that the T as final time is equal to 9.6 seconds. And he has the constant acceleration, and he reached the maximum speed at time t equal to 2.5 seconds. And the information gives that the total length, the total distance is 100 meters. The total distance is 100 meters. We know that the distance is the area under the plot between the velocity and the time. The distance is the area under the plot between the velocity and the time. So if we want to find the area under the plot between the velocity and the time, it seems like we have two regions, the triangle one and the rectangular one. So the area under the plot or the distance for the triangle is equal to 1/2 of the length of in the horizontal length and the vertical length. The horizontal length is 2.5 seconds. The vertical length we still don't know, but is V max. And for the second region, here the area is equal to the area of the rectangle. So it should be the time 9.6 subtract by 2.5 and multiply by V max. And the total distance is 100 meters. And what we need to solve for is the V max. So yeah, we can solve this equation to obtain the V max. It's easy, right? Okay. So you can see that in some problem, you need to do a lot integration with the limit of the integration. See the plot, but in this problem, the challenge is that how did you understand the meaning of the velocity profile? How is the velocity change against the time? If you can draw this picture, you can make everything easy. The equation to solve this problem is very easy. Yeah, it depends on your understanding. And this is the final example for today's class. You still fine, right? Again, we have some complication in the unit here. Okay, we will read it together. A bumper. This is a bumper. And this is something that hit the bumper. And it has the initial speed in the positive x direction. It has the initial speed. Maybe try to make it to be we're gonna make it to be V0 initial speed equal to 40 meters per second. And it hit with the bumper. And after that, after it hit with the bumper, the object is going to the right-hand side in the positive x direction. And then it tries to compress the spring, these two springs. The spring tries to resist the motion of an object. The object is going to the right-hand side, but the spring tries to resist the motion. And it provides the deceleration to the moving object. And do you know the Hooke law, right? You know the Hooke law. So the Hooke law is the spring force is equal to the spring constant multiplied by the displacement or the deformation of the spring. So in this case, if we go further to the right-hand side, we have more compression to the spring. And the spring will create a bigger force with a constant rate of the stiffness of the spring. So with the constant stiffness, the force has the linear relationship with the displacement. But you know that the force has the relationship with the mass multiplied by the acceleration. So it seems like the mass multiplied by the acceleration can be related to the spring constant and the spring displacement, which means that the acceleration itself can be written in the terms of some constant spring stiffness divided by the mass and multiplied by the displacement. And we can say that acceleration also has the linear relationship with the displacement. Something like this. And this constant is the slope of the relationship between the acceleration. The deceleration is the minus of the acceleration. Or if you want to make you too easy to understand, you may like they are plotting the magnitude and show it in the positive value. It's also fine to think in this way to check about this plot, but to check the math, the sign in the math may make you like confused, but you need to understand the physical meaning that the spring try to decelerate an object. So yeah, it decelerates in the positive magnitude, but for the direction, you need to see in the physical meaning of the problem. Now we are talking about this region when the two springs deform. But when it go further than this length, the plate here will begin to touch with the third spring. And the third spring will add more stiffness to help decelerating an object. And with the help of the third spring, the slope of the deceleration will increase, depend on the stiffness of the third spring. So they give the initial velocity of an object, and they give the information of the acceleration. We know the A1 as a function of x, and we also know A2 as a function of x. The A1 when x is between 0 and 6. Okay, let's change this to meter. Change the acceleration to meter per sec square. The magnitude may not like so realistic, but yeah, just make us understand the concept and with a less confusion about the unit. The acceleration in the unit of meter per second square and the displacement in the unit of meter. And the acceleration A2 is between x from 6 to 12 meter. The problem gives this information by the plot, but we need to write the mathematical expression for A1 and A2 in the terms of an x also. And what we need to find is the center of the spring increase the deceleration rate when it passed the 6 meter as shown in the graph, and determine the maximum compression of x. So it means that we need to find x max. Now we still don't know that the maximum compression, it will stop in this region before it touching the third spring, or it will go further than 6 meters into this region when the third spring is active. We still don't know, but from what the problem gives here, we are trying to compose the mathematical description of the deceleration function as a function of the x first. So why not we begin with the first region here when x and ax. Okay, in the first region, by using the similar triangle, we have ax subtract by 0 divided by x subtract by 0 equal to 1,000 subtract by 0 divided by 6 subtract by 0, and then you get, okay, ax equal to, I need your help again.
167ครับอาจารย์
โอเคครับ167 and x, right? Okay, it should be correct. Okay, this is the first function in this region. What if the plate go further than this region? The ax in this region, we consider this triangle ABC and ADE instead the similar triangle. So we have the ax subtract by 1,000 divided by x subtract by 6 equal to 3,000 subtract by 1,000 and 12 subtract by 6, and we need to write down. Can you help me compute this? 2,000 divided by 6, it should be 334, right? Oh. Yeah, you need to help me to do the cross check, but I think it's not a big
มัน
Yeah.
333อะครับอาจารย์แต่ก็ได้เหมือนกัน ไม่เป็นไร
Okay.
Maybe.
Okay. Yeah, you should write. Okay, like this. And yeah, we can write down ax as 3 x and plus or minus, it should be minus 1000. I don't know, minus something, but you can compose the function number 2 also. And yeah, let's see whether it will stop in which region. But again, I want to remind you that in this case, the acceleration is not constant. So please ignore what you learned before from the physics class or high school lesson. Forget that formula to easily use. It's not useful or not simple to use in this problem, but please take advantage on what we just get when we need to deal with a problem with non-constant acceleration. So in this case, we have okay, A equal to dv by dt, and it's equal to dv by ds by dt. So the integration of A ds is equal to the integration of v dv. We don't have enough space. We will bring this relationship and this two equations to the next page. Okay. The integral of ADS equal to the integral of the v dv, and in the first region, the acceleration has a relationship with the displacement by this equation. Ax equal to 167x, and the second one, Ax is equal to 333x subtract by 1000. Yeah, please spend your time to cross check the constant again. I may make some mistake during the calculation, but it's not important now. One thing that I think we forget is if we consider the positive x direction is on the right hand side, do you have any idea about the sign of the equation in the equation 1 and equation 2? Is the current form of the equation has the correct meaning or not? The acceleration should get bigger in a positive x direction, but the direction of the acceleration should go to the left hand side or to the minus x direction. So we need to put the minus here. And also for the second equation also, we should put the minus like here. Okay, from this relationship, the displacement s we consider in the x direction, not in the y, not in the z direction. We consider in the x direction only. So the integral of the a as a function of x dx is equal to the integration of v dv. And for this region, we are going to do in this region first. The integration from x equal to 0 to x equal to 6 meters. The velocity also, we have the initial velocity at time t equal to 0 and some velocity that relate to this velocity is related to the position of x equal to 6 meters. Okay, now the ax is this function. So the integration of minus 167x dx
ครับ
ครับ
ax ทำไมต้องใส่ลบนะครับทั้งสองสมการ
Okay. Because in this case, the positive direction is to the right hand side and the object is going to the right hand side. The velocity is positive.
Chompat is the host now.
สวัสดีครับอาจารย์
อาจารย์จอมครับสอนต่อหนะครับ
ไปไหนวะเนี่ย
จอมมึงเป็นโฮสต์แล้ว จอม
ไม่ทำไมกูกลายเป็นโฮสต์อ่ะ
มึงเป็นคนเรคคอร์ดด้วย จอม
ไอ้เหี้ยหลอนจัดอาจารย์หายไปไหนวะ
เขาน่าจะหลุดเขาน่าจะหลุ
โอ้
ด
Hey, I'm sorry, I'm coming back. I have problem with my network. Do you hear me?
yes
Okay, I'm sorry, very sorry. I will reopen the PowerPoint from now. Do you understand my explanation why we need to have the negative sign for the acceleration?
เมื่อกี้มันหลุดไปตรงนั้นนะครับ
Okay. Because our motion, we define the positive x direction to the right hand side. We define the positive direction to the right hand side. And if you see in the real phenomena, the object has positive velocity to the right hand side, but the spring try to decelerate the object. So the acceleration, the direction of the acceleration is going toward the left hand side in the negative x direction. So if we consider the magnitude, if we consider only the magnitude of the acceleration, we get this number. But if we consider the direction of the acceleration, we know that the object will go slower because the acceleration is go to the left hand side, and we should put the negative side here. Yeah, this is the explanation. Do you still confused?
โอเคนะครับ
Yeah. So by this plot, if I say I'm going to write an acceleration plot, this is deceleration, right? If I'm going to write an acceleration plot, I should write it in the terms of x and the magnitude of the acceleration, but it should go backward. Like this. But they just want us to like not have much confusion on the negative y axis of the value. So they try to switch the magnitude to be the positive, but the real physical meaning, this the right deceleration. If we write it as the acceleration, it should be on the negative side. If you try to obtain the equation, the mathematical explanation of the acceleration for 1 and 2, I think we're gonna got this, the same one, have the negative side here. Yeah, this is the explanation. And yes, for the integral, we do the integral of the first equation by dx, and the limit of integral from x equal to 0 to 6. And on the right hand side, it should equal to v square per 2. From v0, we know that v0 equal to 40. And v, when it passed the point of 6 meter deformation, and by this we know that we can do the integration, and x squared divided by 2, and from 0 to 6 equal to the right hand side also v, that is unknown, divided by 2, v at x equal to 0, which is unknown, and subtract by 40 square divided by 2. From this, when you substitute the value into here, you can compute the value of v. Is there any guy can help me compute the value of
อาจารย์
v? ครับ
อาจารย์ครับ ข้อนี้มันถาม this question asks for x maximum
Yes.
compression x
yes,
so
yes.
maybe we should change 6 to x and let v
No,
to be 0 like the
okay, I get your meaning, but okay, it has two way to do that. I mean, you correct that they ask for the x, right? And we have two way to do that. Our first possible assumption is the system stops somewhere between here, right? If the system stops somewhere between here, we can put v to be 0 and x to be somewhere between 0 and 6, and x can be an unknown. We can do in that way, but my assumption is it may stop somewhere between here. And if it's going to be like that, we need to see some velocity as the initial velocity in the state at this point. It means that when it moves to the 6 meter, it still have velocity. The velocity is still not the 0. So this is like my assumption to this problem. But we may try to see, maybe you correct, and we don't need to go far in this example. If we try your suggestion, it needs to be the integral from 0 to some possible x in this region, and equal to the v square per 2, but the v will begin from 40 meter per second, and the final velocity is 0. It should be somewhere that v becomes 0 and x should be somewhere. If we solve with your suggestion, and the x that we compute is between 0 and x. If we have x between 0 and 6, your calculation is satisfied if we can find x somewhere between 0 and 6. Your calculation is satisfied because the system stops somewhere between 0 and 6, and we only use one equation for the acceleration. We can find x, but if you do the calculation from this and x is more than 6, it means that x goes somewhere in the second region, and we cannot get the answer by this because we need to consider the second equation of the acceleration, and we may need to switch back to the solution that I suggest first. Can we do the computation of this by now? Yeah, I need your help to compute x for this equation.
About 3.1.
Oh, really? Oh, 3 per 1, right?
3 point something.
Oh, okay. So if it just 3,
3.10.
okay, if it's 3.10, so you correct in this problem because the x is in the first region and we didn't see the effect of the second region. So with this case, you correct. So what do you think we will see from my method here? If the x is between 0 and 6, if we continue from this, what do you think we will see from here? If x equal to 6 and v is unknown, v at x equal to 6 is unknown, what do you think we will see from here? Can you help me compute the v at x equal to 6 by this equation? Can you help me?
That should be 0.
By physical meaning it can be, but by math we can see something weird.
It's imaginary.
Yes,
if we do that.
you can see that, right? Because in the square root is negative, right?
Yeah.
So it means that if you're going with some assumption and with my assumption, but the assumption is not true because it's not go further than that, during your calculation, you will see the negative sign in the square root and you cannot compute for that velocity because it stopped before that. But you know that I run through the first method, not the second method, not because it's correct, but how to say,
Is it because the question set like that?
No. Not about the concept also. I want to give you one homework. But you don't need to submit this homework. With this number, it's going into your case, and we can see that if we go from the first method, we can see the negative in the square root, and we cannot find the velocity. Try to modify something to the problem. Let's change the problem here from 6 to be 0.5 meter and change the 12 to 1 meter. Try to cross-check by changing the thing in the problem and continue with the first method. I think if you change the value here, we can see it stop in the second region, and you may not see the negative in the square root, and we can continue. Yes, but for this problem, your solution is simple and not see the confusion. Yes. So try to check when we change from 6 to 0.5 meter and 12 to 1 meter. and we will have some few discussion about this again in next week, like what happened. Do you think you have the
อาจารย์
idea
ครับ
ครับ
or it doesn't work because at first it's feet per sec square and we change to meter, and for the x it's inches and we change to meter, so the unit is too big, so it gives the negative.
Yeah, maybe. Yeah, but yeah, you're right. But as I said, try to drop down, try to reduce the numerical value of this to this, and try to check again if it corresponds to the stop region in the second region or not. And if we change the value to be this, maybe here we can still calculate the velocity when x equal to 0.5. We may still can see the velocity when x equal to 0.5, and we need to do the same process for the second region to obtain the final x position. But to find the final x position, we need to do the limit integral from the medium point to the final point x that is unknown, which is the thing that your friend give the suggestion. But yeah, I didn't have a well prepare on the numerical calculation and create some confusion. So please spend time to recheck about the number. If you try to use 0.5 meter and 1 meter again, and in next week, we will have the complete explanation on the possible case of this calculation. Actually, that's all for me. I prepare all these 3 examples for you today. Do you still have any question?
If we're gonna change the limit to like 0.5 and 1, should we also change the deceleration? It might be too big if that's like 3,000 meters per second squared.
Let me confirm. No, I think it's still fine with the deceleration. I mean, you know that the order that about 3 feet is equal to 1 meter. About 3 feet is equal to 1 meter. It's still in the same range, but if we consider the inch and the, let me see, 6 inch and 0.5 meter is also in the same range. Actually, I prepare this calculation from another version of the textbook, and it comes from the SI unit. And the image that I use here, it comes from different version of the textbook. And in the textbook that I prepare the computation, the number here is 3,000 meter per sec square and 1,000 meter per sec square. And these 2 values are 0.5 and 1. And I think it's gonna stop in the second region. I may want to like try to compute the numerical value and check the case. Yeah.
Okay.
ครับ โอเคไหมครับวันนี้
โอเคครับ
เฮ้ยสอนแบบนี้มันดูหนักหน่วงเกินไปปะวะหรือว่าพอได้อยู่
ได้อยู่ครับ
แต่คิดว่าคาบต่อไปก็จะพยายามสอนให้เลิกเร็วขึ้น แล้วก็ตัวอย่างอาจจะไม่เยอะมากแล้วกันครับ แต่ว่าตอนสอบจริงๆไม่น่าจะยากอ่ะก็คือผมน่าจะสอนใส่เนื้อหาเยอะหน่อย แต่ว่าตอนสอนจริงตอนสอบจริงไม่น่าจะยากก็ไม่ต้องเครียดกันมาก แต่มีเวลาก็ไปลองเช็คเพิ่มไอ้ที่สอนไปแล้วกันครับyeah, for translation to some foreign student, I mean, in the class, I may give you a lot example and try to teach hard, but in the exam, I don't think you should worry. I mean, it's not that difficult. And good luck. Thank you for today. I'm
Thank you,
going
teacher.
to
Thank you
ขอบคุณครับ
สวัสดีครับอาจารย์ครับสวัสดีครับ
สวัสดีครับ บ๊ายบาย
ส
ค
วั
รั
ส
บ
ดีครับครับ
สวัสดีครับ
ครับผม
อาจารย์ครับปกติอาจารย์โพสเรคคอร์ดไว้ในไหนป่ะนะครับ